The topic that we'll be discussing today now is pressure. The prerequisite topics are forces and the concept of area that we have already discussed um, before. Before into this new topic, it's very important to, before getting into the scientific concept or the scientific formula of pressure, it is very important to first understand how we use the word pressure in our daily lives and how it relates to the scientific um concept or the scientific formula of pressure. So, to make sense of some effects of pressure in which a force acts on a body, we have to consider not only the force but also the area, also the surface on which it acts. For example, the skis prevent you from sinking into soft snow because your weight is spread over a large area. In this case, the weight exactly is the force, and the area of the skis pair of skis is basically the area. So the reason why their length is spread over a large area because we want greater pressure, greater area, hence less pressure. So we say that hence the pressure is less. Now, before we get into this concept of how less area is gonna increase the pressure or how greater area is going to decrease the pressure, I think it's important to note how we use the word pressure in our daily life when we're talking about our chores or tasks. If someone has a lot on their plate, so we say that um, I have a lot of pressure. Let's just say I have a lot on my plate and I have a lot of work to do. I have a very busy schedule. I say that I have a lot of pressure because I have a lot on my plate. So we tend to say that it really indicates that when someone with less capacity or less storage or are given so much more load than what they can afford, we tend to say that they have a lot of pressure or in terms of how stressed they are. Now, we if we use this concept in terms of science and the concept of pressure, uh, it gives us the idea of how if we exert a very large amount of force on a very localized small area, the pressure on that specific object or that specific point is really large. So now it's clear by now that pressure is the force acting on unit area, and it is calculated from the formula that pressure is equal to force divided by area. The unit of pressure is pascals and it equals to 1 Newton per square meter, and it is quite a small pressure. So basically, uh, pascals is the SI unit and of pressure, um, and it equals to it equals to Newton per square meter if you're talking about the SI units. And if we simplify that further to the base units, then we can put it in form of kilogram meters or seconds, and then it will form. Okay, we can do that over here. So Newton is basically mass into area. So kilogram meters per second squared per square meter per square meter. Now this negative indices basically show per or fraction per square meter. So this cuts and this makes it -1. So basically the SI unit of pressure is pascals, which can also be noted as Newton per square meter and also as Newton per meter second squared. Per meter per second squared. So that's how it is. Moving on, an apple in your head exerts about in your hand exerts about 1,000 pascals. Now, the fact why it's written over here that pascals is a very small unit of pressure. However, it is the SI unit but it is a very small unit of pressure, and in most of the daily life scenarios, the pressure that we'll be dealing with is in thousands or megapascals. For example, the atmospheric pressure is also 10 raised to power 5 pascals. So, however, this is the SI unit, but we tend to add prefixes in order to make it a lesser manageable number. So, an apple in your hand exerts about 1000 pascals. The greater the area over which a force acts, the lesser the pressure. This is why a tractor with wide wheels can move over very soft ground. The pressure is large when the area is small, and this is why nails are made with sharp points. Um, the reason why when we hammer and just a little point of a metallic object makes such a huge impact over a sudden impactful force is because we have is because of this area. Now, the nails could have been all vertical or cylindrical in shape. However, they are not. They are um, converged into this needle-like shape or this point at the end because of the impact we need. So what happens is when you apply an impactful force on the head of the nail, the force is localized at this exact point and it magnifies the impact. So that basically is the concept of pressure and how we can tweak the area or the area distribution accordingly, with the kind of pressure distribution we want on an area or on an object. So now, this is a very interesting example that over here we have a same box, 4 multiplied by 3 multiplied by 2 box, 4 into 3 multiplied by 2 box. Now these are the dimensions of the box um, with height, length, and width respectively. What, sorry, respectively. So what happens is that this object is basically of 24 newton, which means it's about 2.4 kg. Now what happens is we tend to say that this object will have the same impact when it is on the ground or when it is on some surface, but we can really see a very different concept over here, that when this object right here is held in this position where the surface that is touching the ground is 3 into 2 surface, this surface, then the pressure that it exerts on the ground is uh, so much more greater than when it is held in this position in which 3 by 4 the larger surface is on the ground. So it really gives an idea of how the contact surface, this surface is called the contact surface, really has a huge impact on um, the pressure that is being exerted on the ground or on the surfaces where it is put. So, um, in this case, the contact surface is has the contact surface area has magnitude of 6. Over here, it has the magnitude of 12. So this is double the area. Hence, we have half the pressure. Since pressure is equal to force divided by area, this really tells us that when area doubles, pressure should halve, because pressure is directly proportional to force and it is inversely proportional to the area. Now, moving on from this example, let's talk about liquid pressure and how we measure it and what kinds of devices are used. And it's a really important topic. Okay, so liquid pressure. Pressure in a liquid increases with depth because the further down you go, the greater the weight of liquid above. In figure A, water spurts out fastest and furthest from the lower hole. Now, you can really see It says that pressure in a liquid increases with depth. So pressure, we can just write that pressure is directly proportional to the height or the depth. So let's just put it as h. Um, because further down you go, so that means that the datum, the point of reference that we are going to consider, because we are talking about depth, is at the start of the surface. So this is the datum point, and we're gonna measure from here downwards, right? So the first point, the least height or the least depth that we have over here is at this point. You can really see that the flow or the pressure is not that much, and hence why the liquid is just very slowly just going off in this direction. It is not really going in some force like this, or like in form of a jet, or in form of a forced flow. It's really unforced, and it's really limp, as you can see. However, the greater the depth is, you can see that the more pressurized the liquid becomes, and it really indicates how pressure is directly proportional to the depth it has. Okay, the next concept that we have is that pressure at one depth actually is it acts equally in all directions. The can of water in figure B has similar holes all around it, and it is on the same level. Now, uh, it's really important to note that even if the the can had different surface over here, or a different surface over here, or anywhere else, the pressure that acts at one level or at a certain depth is going to be the same no matter what direction we are talking about. So we're taking into consideration the whole 360 in this can. However, because of two-dimensional diagram, we can only see three holes. But um, even from the holes that cannot be seen in this diagram, the pressure at which these water jets are coming out, that's supposed to be the same. So that tells us that pressure in all directions is the same. The can of water in figure B has similar holes all around it at the same level. Water comes out equally fast and spreads equally far from each hole. Hence, the pressure exerted by the water at this depth is the same in all directions. Okay, so now that we've talked about the same direction, and also its how it is related to height, we know two things. Number one, that pressure in liquids is directly proportional to depth, in which the upper part or the meniscus of the whatever object or whatever instrument we're using is the reference point, because we are going to go down as we increase in depth. And the second point is that pressure P1 is equal to P2 is equal to P2 is equal to P3 if they have same depth. So that basically means that whatever the direction, whatever the material, the really thing that depends is the depth. So same depth, and also let's just write that it is same in all all directions. Okay. A liquid finds its own level. In the YouTube of figure A, the liquid pressure at the foot of P is greater than that at the foot of Q, because the left-hand column is higher than the right-hand one. Now, although both of these liquids, they are introduced, or they are in the same atmosphere, however, we can really see how, or they might not be in the same atmosphere. The thing to be noted is that liquids define their own level. They settle at some point where they find the equilibrium of pressure that is being exerted from the upper side and from the lower side. So the foot of P is greater than the foot of Q. So that means this foot of P is greater than that of foot of Q because the left hand column is higher than the right hand column. So that's another thing to note. When the clip is opened, the liquid flows from P to Q until the pressure and the level are the same. The liquid finds its own level. So initially, this clip is just locked, but when it's open and these two liquids are allowed to mix together, then what happens is that liquid finds its own level. It really does not matter what area of the tube is or whatever. The liquid is going to find its own level, and the both are going to settle at the same level because they are both, provided they are both at the same atmospheric pressure or whatever pressure they have. So in this case, as both of these tubes are open to environment, we can assume that they both are at the same pressure, and hence why when the clip is open, they'll find their own level. So this is our fourth point, that the liquid finds its own level. Moving on, although the weight of liquid in Q is now greater than that in P, it acts over a greater area because Q is wider. So it explains in both terms, in terms of finding its own level and also in terms of the pressure distribution that we have already studied, or the pressure formula that we've studied, that pressure is equal to force divided by the area. That even though the height of the look if the thin tube and the thicker tube both have the same level of liquid, it's very easy to note that obviously the weight of liquid in the thicker tube is going to be heavier because the height is same and the cross section area of the Q tube or the thicker tube is greater. So height multiplied by the cross section area gives us the volume, and then volume, from that same density we find the mass, and then from mass we get the weight. So the idea is that obviously the force exerted by the thicker tube, by the liquid in the thicker tube or the wider tube, is going to be greater. But the reason why it justifies these liquids being on the same level is that we have to divide it by cross section area again to find out the pressure. So even if you divide the higher weight of liquid divided by the cross section area or the surface area where it acts, will in turn again get the same pressure for P or for Q. Okay, so the last 6 point is that in figure B, the liquid is at the same level in each tube and confirms that pressure at the foot of a liquid column depends only on the vertical depth of the liquid and not on the width or the shape. Now in this tube, you can see that there are different shapes, there are different cross sections, there are different widths of the tube, and also that not all of them are completely vertical or completely horizontal, or or just at the same angle. This one is just slanted, this one is curved and it has a bump in it, and this one has this other random wiggly shape. So the thing to note in all of these scenarios is that they settle at the same level. So the very important thing is again the height. It doesn't matter what kind of width it is, what kind of shape it is. What matters is the height when it comes to liquid pressure or the depth. Pressure depends on the density of the liquid. The denser the liquid, the greater the pressure at any point. So the thing to note is that in this scenario, if the liquid in P and liquid in Q weren't the same liquids and were different, then obviously their density would have been different. So if their density was different, that's very much you need to note that obviously if their density is different, then they wouldn't settle at the same level, and it's not fair to compare them because they're different materials. So pressure also depends on the density of the liquid. The denser the liquid, the greater the pressure at any given depth. So another thing to note is the pressure is directly proportional to depth, and it is proportional directly proportional to the density. So depth and density. Okay. Now, we've talked about the main general concepts of liquid pressure. Let's talk about an application of liquid pressure, that is the water supply system. A town's water supply system often comes from a reservoir of higher ground. The water flows from it through pipes to any tap or storage tank that is below the level of water in the reservoir. So, a town's water supply often comes to from a reservoir. This is a reservoir. This is at a higher ground. Water flows from it from pipes to the storage tank. Let's just say, and it's very important to note that the storage tank is at a lower level or lower altitude, that is below the level of water in the reservoir. The lower the place supplied, the greater the work pressure. In the very tall buildings, it may be necessary first to pump the water to a large tank in the roof. Reservoirs for water supply or for hydroelectric power stations are often made in mountains regions by building a dam at one end. So what happens is that if you already build it in, a place where the terrain is already mountainous or something, so there's less investment cost, and it gives the difference in height is already given, and you can just install the reservoir and the storage tanks on them. So that's basically another thing. So pressure is also a huge factor, that the more height it falls from, the greater pressure it has, hence the greater energy it has. Similar is the case with hydraulic machines. Liquids are almost incompressible, that their volume cannot be reduced when they're squeezed, and they pass on any pressure applied to them. So if I apply some pressure to this piece of liquid or whatever, and then I run a piston through it, so I give it some pressure, then it will definitely um, deliver the complete pressure to this piston or whatever that is attached next to it, or that it is applying the force on. So, uses made of these facts in hydraulic machines. Figure shows the principle. Okay, so this is the figure, and I should delete these. Okay, so again, we are basically using liquid as a medium to transfer the pressure or the force that is being applied from one side to the other, and we can really use this uh, concept to change, decrease, or increase the value of force that we want to exert on one area. So let's just say if we're applying force on this side, and then I want to apply some lesser force on this side. Now, what happens is that the pressure is going to remain the same, as the liquid is incompressible and it's going to transfer the complete pressure, but the force over this side that it's going to exert and the load is going to be lesser because the area is greater. So we can really, utilize this fact or these concepts of area relation with force or pressure, and the fact that liquids are incompressible to really make use of it in terms of hydraulic machines. So suppose a downward force act. Now this is going to just explain what happened in the previous slide and how hydraulic machines work. So suppose a downward force F acts on a piston of area A. The pressure transmitted through the liquid is pressure is equal to force divided by area. The pressure transmitted through the liquid is pressure is equal to force by area. This pressure acts on a second piston of larger area, producing an upward force F is equal to pressure multiplied by A. Since A is larger than the smaller A, F must be larger than the other F, and the hydraulic system is a force multiplier. The multiplying factor is A divided by A. A hydraulic jack has a platform on top of piston B, and it is used in garages or to lift cars. Both the valves open only to the right, and they allow B to be raised on a long way when A moves up, down repeatedly. So that's how it basically works. This is it. In the next topic, I will be explaining the concepts of pressure. We'll be talking about the liquid pressure and the instruments that are basically used to measure pressure. and how we can use them to even compare different pressures and different scenarios.